was presented by Kimmo Ahola. We are now starting to talk about some of the projects and achievements made in the projects, and one of those projects called Esonia. Actually, results discussed during this presentation came as a chain, or as a result of a chain of the projects, many of those supported by Ubicom and Tekes. So, my name is Andrei Lobov, as was presented. I'm with Tampere University of Technology, FAST laboratory, and you can see the web address, www.tut.fi/fast. There you can check some of the videos from the YouTube channel, so one of things to consider. And the subject, how Internet of Everything is set to revolutionize the industrial and M2M, machine-to-machine sector. I start with some definition, pick up from various sources, this from SAP. So we have a world of physical objects that are supposed to be seamlessly integrated to become objects active in business processes. So these are called smart objects. And one of the studies made by Cisco predicted that 99% of physical devices, things, are still not connected to the network, and therefore there is a huge potential for the growth. And here is a number, $14.4 trillion of new value. And what is important here, at least for us, is that manufacturing sector, which accounts for the largest amount, 27%. So, and this, according to Cisco, new term, will result in Internet of Everything. And I wanted to start with some examples and of the things, of Internet of Things, and I just bring here one example, application example by Kobachi. So this is a device measuring soil for the plant sensors, measuring the humidity, temperature, light, so basic sensors embedded. So, however, it's working one way. You can have your application embedded and monitoring values sent by the plant or by the soil, and to know when, for instance, you need to water the plant. However, it's not only things that are possible. So to have a real closed loop, in this case, some people, let me see if it works, make it possible even to generate sounds. Let's see. Okay. Now what you are hearing is sensors integrated with the plant. Small currents are taken from the plant, and, well, you can give somehow a feedback. Okay, so it's this work done as a reference, University of Minho in Portugal. So where it all brings us, we start to see that physical systems becomes more complicated, and really you are able to measure and collect information from applications which were, well, not possible beforehand. And now coming to the problem domain, it's industrial automation. I'm with the FAST laboratory, which stands actually for Factory Automation and Automation Systems and Technologies Laboratory, and our problem domain is industrial automation. And there we have such kind of systems like a production line, seen in the upper right corner, like equipment used in discrete manufacturing, producing the pieces, and probably in the process industry, having a different kind of system, piping system, for instance, controlling the flow of liquids, as example. So, and in this domain, there are very conservative people and very strict rules for system development. And to bring innovation to this area or new technologies to this area was a challenge. And I would like to put here for understanding a timeline how developments were made. So I will start with the 60s. In the 60s, there was first computers, dedicated computers for industrial automation introduced, called PLCs in our domain, Programmable Logic Controller, which is basically a box, well, embedded device having a set of inputs, output, digital inputs and outputs, or analog analog inputs and outputs, and can be programmed through the terminal, can be written and rewritten the programs on the device. Okay, and with the black color on this slide, on this staircase, I have noted events that happened in industrial automation domain, and with the blue color, I would call it this in general IT sector. And we could see that certain things coincide or in certain points start to influence each other as those domains evolve simultaneously. So before that, the systems were made with the relays, so very basic components having a metal plate moving as there is a current on the control inputs appears, and either the contact can be closed or open. So, and those systems initially were hardwired. So if problem in this hardwired relay system occurs, an engineer should go wire by wire to localize the problem. So the introduction of dedicated computer allowed to go away from this problem, and by searching problems in the program, simplify the life of engineering. Then in the 60s, what has also happened, ARPANET emerged, prototype or foundation for future internet. Then in 70s, we could say that we saw in the industrial automation world start the miniaturization of the devices. So smaller PLCs start to appear. First attempts network protocols for integrating industrial automation system emerged. Also in the 70s, more close to the end, first personal computers were born. And moving to the 80s, first standardization attempt of communication came up, so it's called Manufacturing Automation Protocol, called MAP. And at the beginning of 80s, Ethernet appeared as a joint work. And 90s saw the attempt of standardizing dedicated programming languages, how we develop programs for industrial systems. There are no those general purpose programming languages like C, Java, Pascal, whatever. So rather, there are dedicated programming languages, and there is a particular standard for standardizing them. Also in the 90s, we can say that internet started to take whole speed of integrating people working on the Ethernet-based network as a backbone for internet networks. And in the last decade, we can say that web standards-based application in IT world start to take a place, giving the rise for SOA-oriented architectures and, in general, Internet of Things application. Also, in industrial automation world, dedicated standards such as IEC 64099 emerged. So, what can be noticed here that we end up in the devices used for the industrial automation, which are now capable of running deterministic control of the process or the controlled objects where they're connected for the IOs, inputs, outputs, and at the same time are enhanced with the modern or latest web standard-based protocols. So what was the result at the end? That we are able nowadays to simplify or ease vertical integration of applications, so to get from the physical layer, from the device layer, information almost literally to any place of the world, if we would like to. So to connect our systems to the internet. And I would like to give an example of one of those technologies, what we used, called 6LoWPAN, IP version 6 for over low power area networks. And our lab was the first one using IP version 6, 6LoWPAN for the industrial for factory flow implementations. So here you can see an example of the protocol stack. Well, what are the benefits? It opens possibilities for integration, simplifies the integration, and again allows vertical integration. And as standard was developed, there came on the market certain devices appeared. One of them, example, is Inico devices, and this includes like temperature, humidity, light sensors, digital I/O devices, so for collecting digital inputs and analog inputs. And example is using MEMS technology, gyro or accelerometer application, and along with the wireless routers. So some details on the technical, some technical details, sorry, on the operating system is ContiQ/OS, hardware Atmel, and it's, well, as I said, fully IP version 6 compatible. And we have found out that use of the latest standards allows us to find new applications, and one of the applications I would like to present here, it's called Advanced Pallet Information System. Pallet is a product carrier in the system, in the automation system, and it goes, here you can see different cells, automatic cells, and as a pallet travels through it, you can localize where the product is located. So what is new about it, or what is what we were able to find out? For instance, how in the traditional system this problem is solved, pallet localization. It's sensors installed, positioning sensors, well, inductive sensors to locate when at certain places product arrives, right, and see if it's present. Then, of course, those lines can be embedded with the RFID readers to read information, what product there is, what assembly operations it requires, etc. But in certain cases, it's not enough, and we can use additional information to improve our localization system. And this additional information was thanks to the gyroscopes and accelerometers, showing us what is current location of the pallet. Okay, this is just the interface of the system showing where the pallet goes through, and I think I will prefer to going for the video for this presentation. So what you will see here in the video is a pallet which is equipped with a positioning device like this. And let me go to the right location of the video. Sorry. Yes. So you see the pallet flows in the system, and giving an equipment, this accelerometer to the pallet, having 6LoWPAN stack on it, connecting to the wireless router, we can get an events. Here are examples of events. Pallet stopped, pallet moved, pallet tilted to different directions, so X, Y, Z directions. And once you see in the real time, events are sent as pallets turns, and in the advanced pallet information systems, we can predict, or well, actually give the location of current location of the pallet. Of course, this includes or this requires to have a model of physical layout in this case. Okay, so what kind of problems it solved? So it's enhanced sensor capabilities of the production line and allows to detect abnormal behaviors. For example, if a pallet suddenly disappears in certain locations where it shouldn't disappear, so it can be detected. So for instance, if personnel have taken the product from the line and, well, stored somewhere where it's not supposed to be. So it's, therefore, system allows to trace back where abnormal situations have took place and identify the cause of the problem. And in addition, this kind of system allow us to collect different other key performance indicators, knowing, for instance, what are the current processes to be executed, and providing greater visibility of our production line with embedded interfaces, providing different statistic information, pie chart, and in general, allowing us simplifying the integration of our system. This became possible due to so-called loosely coupled integration provided by the protocols we use. And one important message here is that development of ICT technologies, and in particular communication technologies, make it affordable for the industrial application to use remote computational resources. So by telling this, I mean that, for instance, first industrial protocols such as Profibus, DeviceNet, have very low data rate in terms of 1 megabit per second, 50 kilobits per second. And historically, they have stayed there. But thanks to advance of the internet-based protocols start to enter industrial automation domain, and thanks to the high communication data rates, it's possible to transfer large amount of data, provide extended user experience information, while still keeping our devices running deterministically. And new applications for the industrial environment starts to emerge. However, we envision there are still improvements required for device integration, for instance, development of new tools and frameworks to allow factory floor engineers to get accustomed to the Internet of Things. Thank you very much.